And so I just express it as f prime g prime equals to the identity. In other words, f prime inverse, I don't know if that really helps us or not. Okay, well, I mean, what I write in the notes is true. I claim that that implies 5. Is it clear? So I'm saying something, right? I'm saying that. So what I'm claiming is apparently. Well, check this out. F equals to y composed with x inverse, right? Has, you know, the component function. What is the component function of this? It's that, right? Like that's the component function of that map. So my larger point is that the Jacobian of f is literally this thing. And likewise, the Jacobian of g, right? The Jacobian of g is the matrix that has these guys as components. But we know that these are inverse functions, and therefore they're Jacobian matrices suitably evaluated, right? Are inverse matrices, but that was the claim. That is exactly what 5 claims, right? Now, I say evaluated at p on both of them in the claim, right? How does that sort out here exactly? So let's see here. Let me write out in stupidly gory detail. We're supposed to do Jacobian of f at g of p, right? Times the Jacobian of g at p. So g of p is what? I believe it all simplifies down to just be evaluation at p when you look at it. I'm sorry, my mind is just slightly foggy on this. I don't feel like I'm going to offer you anything of value beyond where we are on this point. All right, so that's pretty much that. Let's go on. The proof of 6 is interesting. Let's look at that. So I've only left you the product rule for homework. I guess if I was more adventurous, I would leave some of these chain rule ones for students, but I have a feeling that it's just a little bit too much for you guys, given the time constraints of undergraduate life. So that's why I do them here. Partial f partial yj at the point P is by definition partial partial w upper j of f composed with y inverse of w. And then you take that and you evaluate that guy at y of p after you're done differentiating. But then the trick, as is always the trick when you're trying to derive a chain rule, is to insert the number 1 cleverly. So what we do is we go, oh, well, that's the same as the derivative of f composed with, looks like you need an x inverse there, doesn't it? So we just stick in an x inverse there. But you can't just do that on its lonesome, right? You've got to do what? X inverse composed with x, composed with y inverse, right, of w. And we can do that because of the assumption of the overlaps of the chart domains that we made. We're still talking about the common pair of chart domains at P. And then I go, oh, okay, well, this is really partial wj of f composed with x inverse of u1 of w, u2 of w, um of w, right? Such that evaluate yp, and here where w equals to what? Well, where u of w is x composed with y inverse of w. Or if you like, I can say the kth component of that is the kth component of this. That is, after all, x composed with y inverse is a transition function, right? If you go back to this picture, x composed to y inverse would be like this, right? And so since x composed with y inverse is a mapping from Rm to Rm, right? It's a mapping from Rm to Rm. That means that what we're up against over here is a composition of function of Rm, right? And so then I would remind you, we know a chain rule for compositions of functions on Rm, and it looks like the following. Sum k equals 1 to m of partial, goodness gracious here, I'll get it eventually, x composed with y inverse, the kth component of that guy, with respect to the wj. That gets evaluated at y of p, and then times the partial derivative of f composed with x inverse with respect to uk, evaluated where? The inside function, right? So what we're going on, this is the derivative of the inside function. This is the derivative of the outside function, evaluated at the inside function, which here is x composed with y inverse. How do I write here? I guess I write it as y of p, just because, yeah. All right, so then, of course, that simplifies just down to x of p, right? And what we're looking at then is, what is this? Well, this is sum k equals 1 to m. This is partial x upper k, partial yj, evaluated at y of p. And this is exactly partial I'm missing a, am I missing it? No, that's partial f, partial x sub k evaluated at x of p. And that is the chain rule on a manifold. To write it, a little bit more briefly, what we're saying is that the partial derivative of f with respect to yj of f, which is written as a function of, let's say, x upper I, right? Well, I'll just write it as f of x. Well, what's that equal to? Well, it's equal to the sum, k equals 1 to m of partial f partial xk, times partial xk partial yj. This is exactly the chain rule that we teach in Calculus 3. And maybe it doesn't look familiar, but for instance, if I've got, function of two variables differentiating with respect to r, a function of x and y, right? Maybe if I, to make it kind of more like in concert, list them out, like that. Okay, great. So like that, well, what do? You do, okay, so that goes partial f, partial x, partial r, plus partial f, partial y, partial r, right? That's how it does. And that's exactly what the chain rule is on a manifold as well. It is part of the reason that physicists are able to do calculus on manifolds without really knowing. They don't need to know all this, right? Like, if you just assume that it works the same way, well, it does. But there's some careful constructions going on here. Now, to really convince you that the constructions are worthwhile, of course, at some point you need to give an example which really makes explicit the abstract nature of what we're doing. And I probably don't have time for that today, but we will do those calculations. So let's see here. Let me give you a few more theorems, then we'll be done for today, I suppose. It does take a while to prove these things. I think this is time well spent, though, Ernesto. I know what we're doing is kind of a little bit boring, but it's for a good cause. I hope that we have a really concrete understanding of what we mean by the partial derivative on the manifold. But once you have these basic rules of calculus, then all of the, familiar elementary rules of calculus quickly fall into line. Like, what is, well, I guess this isn't about the partial derivatives, this is just about derivations again. But if you've got a constant function, right? If f, an element of C infinity p, is constant function, then xp is an element of the derivations at p and m, right? Then what can you tell me? Then xp acting on f is what? It's 0, right? And how do we prove that? So the proof goes something like this. Let g of x equal to 1 for all x near P, then, you know, fg of x is just equal to, you know, 1 times f of x, which of course is equal to a constant, right? Whatever the constant value is, right? So that gives us, thus, f is equal to fg, right? F is equal to fg. And I seem to be using, maybe instead of x, maybe I should use like a q here or something. This is kind of bad. But this is the abuse. You know, this is the abuse. Is x a point on the manifold, or is x a coordinate chart? Well, is u a point in Rm, or is it the coordinate chart? You see, that's why the abuse is warranted, because we're trying to encourage the same abuses on the manifold that we enjoy on Rm itself. But I think that may exactly be the reason that people find differential geometry challenging, is this abuse is systematic and often unapologized for. But anyway, once you have that, then, well, it's a derivation, right? So if we look at this, it's what? It's f of p xp of g plus g of p xp of f, right? But that's all equal to what? xp of f, right? But what goes on here? F of p is a constant, right? G of p is 1, right? And so what does that do for me? Oh, it looks like this proves that c times xp of g is equal to 0. Oh man, that's not what I wanted. That's not what I wanted. I wanted to show xp of f was 0. But what do? Can you tell me what to do next? It's a derivation, right? So what can we do? But what is c times g? What would we mean by c times g, right? C times g at the point, let's say, I'll use x, is what? C g of x, which is c, which is f of x, right? But that holds for all x near p. This is f. See that? So, and there you go. Another proposition is if fg are in the smooth functions at p and f of x is equal to g of x for all x in V, and xp is a derivation at p of m, then xp of f is equal to xp of g. Well, that's kind of like, well, yeah, duh. But this is interesting, right? That says that the derivation acts the same. I mean, it almost seems Well, you notice what's going on here, though. This is only assuming that the functions are equal near the point. So I'm not saying that they're literally the same functions everywhere. Just if they're equal near the point, on an open set around the point, that's what V is, then that suffices to say that they have the same, that the derivations act the same on them. The way this is proved, then, is simply this. See, if we have f of x minus g of x is equal to, well, it's equal to 0 for all x in V, right? So h equals to f minus g is constant, right? Which then implies that xp of h is equal to 0, but that exactly tells me that xp of f is equal to xp of g because, well, xp of f minus g is xp of f minus xp of g, right? So what we'll prove next time, and this is going to take us significantly longer, so I won't keep you today for this, but next up, we are going to prove that an arbitrary derivation on a smooth manifold necessarily can be written as a linear combination of the partial derivatives on the manifold. So while not every derivation is literally a partial derivative, at least every derivation can be written in the following way. We'll prove that you can just write xp as equal to the sum j equals 1 to m of xp acting on the jth coordinate function times partial xj at the point p. So that is going to basically show us that any derivation can be expanded at the point in the basis of the coordinate derivations. And that is going to lead to a larger story, which is that the coordinate derivations naturally form a basis for what we'll call the tangent space. Now, I guess I really technically should probably talk a little bit about like what we're doing in terms of vectors. Let's go back to that formula for a second. We'll end here today. Hopefully I can make sense of it. Do you remember the formula for the directional derivative in Calc 3? So like the formula for the directional derivative at the point P of f in the like the v direction, it's the gradient of f at the point P dotted with v. Now in Calculus 3 we make the assumption that the v is a unit vector, but we won't make that assumption here. The thing is, what we're really looking at is like a times partial x1 at the point P plus, let's say a1 plus, I guess I should say v1 plus v2 partial x2 at the point P plus plus vm partial xm at the point P. All of that, right? All of that acts on f. That is the directional derivative. So you see there's a natural correspondence then. You can see it from this formula already that we can really, every vector, right, gives us a corresponding derivation. So so one of the things that goes on in manifold theory essentially is that we just take this as our basic concept of what a vector is. Because it's convenient, because we like to think about changes in functions and things, so if our vector is already something that acts on other things we're interested in, that puts us one step closer to interesting concepts, as opposed to just thinking about a vector as some sort of abstract geometric thing, which we don't even know where to draw, because on a curved space, like where does the vector go? Well, it's off the space, so if it's off the space, it's kind of an unintrinsic idea. But on the other hand, a derivative on the space, that's something that's intrinsic to the space. It's something that's baked into the cake of what it means to be a curved space. Like, it's not something we need some sort of, external context to image. There's a heuristic reason for why we do it. I don't know. I think when you read a really master of these things talk about it, it can become more convincing, like if you read Barrett O'Neill's book. But anyway, that's it for today, for this class. So, thanks.